Hello and welcome. In this video, we're going to look at the series parallel circuit here and try to identify what's wrong with it, the fault in the circuit. So the first thing we need to do is identify what we expect from the circuit to get the total current at the beginning here. And we know IT requires our voltage source and our total resistance. So we'll start with RT. RT is equal to, and we'll trace our current path here. The voltage source gives us our perspective here, and we go straight through this first resistor. So it's 120. In series with, since we had no choice, open a parenthesis for that node right there. We can go down to ground through this 200 ohm resistor. So we'll say 200 is in parallel with whatever else is in the circuit. So we continue down and we have no choice but to go through this component here, this 440. So we'll say that that 440 is in series with whatever comes next. And what comes next is in nodes. We'll open another parenthesis in here. And we'll say that that leads us through the 870 and the 680. So we'll say 870 is in parallel with 680. We'll close all those parentheses off and we'll solve it innermost parenthesis first. So let's do that. We'll put our 870 in parallel, so 1 over 870 in parallel with, so we'll add that to the 1 over 680. And after that, we know that that's going to be added to the 440, so we'll say plus 440. And that gives us our new equation here. We can say that we have 120 plus 200 in parallel with this value here of 820. We'll round that up to a 2, 822 ohms. And we can solve for that out now. We can say that we have 120 plus the parallel of, so we'll do 1 over 200 plus 1 over 822. And that gives us 280.8, so we'll round that up to 281. So our RT expected for this circuit is 281 ohms. We can use that to find our total current. We can say that the 280 that we have there and our 12 volt source, so 12 divided by 281 gives us a total current of 42.7 milliamps. So let's check that. So our voltage, or our current probe over here, we'll hit play on that, and we get 47.8. So it is actually, and we get 47.8. So it is actually a little bit larger than what we expect. Let's get rid of some of our pathway here. So let's determine which component is measuring appropriate values and which ones are not. We said that this first 120 ohm is actually in series. That's what we did across the top here. We said that that was in series with, so we put a plus sign after it. So we expect a voltage drop across it, and we expect this current to flow all the way through it. So if we measure down and we watch this current, it's 47.8 milliamps, and we end up on the other side with 47.8 milliamps. So there is current through that, which means we should see a voltage drop. Start at 12 volts, and we should have a voltage drop at the node. 6.27 volts. That's what we expect, right? So this one we can check off as probably okay. This 120. It might be leaking, but it's not open and it's not shorted. So let's keep going. At the node here, we get 6.27 volts, and we know that that is parallel. So voltage in parallel is going to be shared. 6.27 volts goes this direction down to ground. So that's 0 volts at the bottom. And we see that 6.27 volts goes down towards that other branch there. So let's check our current. Let's make sure the current divided in the parallel branch here, because we know that it came down to 47.8 milliamps comes down, and we know that it should divide here. Some of it should go towards this one, and we get most of it towards this one. 31.3 milliamps out of the 47 goes towards this 200 ohm resistor. That actually makes sense because this resistive path down this direction is much smaller than the whole combination of these ones. Because we did solve for that in our Desmos. We said that the combination of the 440 and the parallel down here was actually 821. And if we compare 821 or 22 to the 200 ohm branch, that means that this 200 ohm branch should have more current than the other branches here. So that makes sense, which means that this 200 ohm resistor is probably okay also. So let's keep going. We'll go down this other branch. We see that the remainder comes down towards this bottom branch. So from the 47.8, 31.3 was taken off down this branch, and the remainder, 16.4, goes towards this bottom one. We said that this component here, this 440, was in series with whatever came next. That's what we did, a plus sign after it. So we'll measure across that and we'll see that that 16.4 milliamps does actually make it across that resistor there. So that one's okay. As far as current goes, we just need to make sure that it also has a voltage drop, because we can have current through there with no voltage drop sometimes. Let's measure that. So 6.27 volts at the node, that's what we expected at that node there, and it should drop voltage at the bottom here. And it does not. 6.27 volts on both sides of that. So that's our first flagged one here. And so let's circle that one as a possible fault here, because it does not have a voltage drop. Right, and as we continue on, 6.27 volts leads us down into this bottom branch here. They both get 6.27 volts. So let's check the current because it's in parallel. 16.4 milliamps comes down, 7.2 milliamps goes towards this 870, and 9.2 milliamps goes towards the 880. So these two are splitting current as expected. The 680 has a little bit more than the 870. So those are fine. So our fault here is going to be the short across the 440 ohm resistor because it has no voltage drop, but it does have current. Right? So let's keep going. We've got another fault down here. Let's move down and we'll check this one. This is the same circuit. This circuit, we see that the 120 ohm resistor at the top here should still be in series, so we can check that with our probe lines here. Let's grab those. So we'll measure our current in the circuit. We know what we expected from this. It was supposed to be 42.7 milliamps, and we got 40.9 milliamps. So we actually have more resistance than we expect. Right? That could be a couple of different reasons for that. So let's check and see where we're moving or where we're losing our voltage drop or our current. So this first one here, we've got 12 volts at the top of this resistor. We expect this to be a series resistor, so we should have voltage drop and current flow. So our 40.9 should be on both sides of this resistor, and it is, so that's okay. The current is fine through there, so the voltage drop should appear across this resistor also, 12 volts on top, 7.9 on bottom. So this resistor at the top here is probably okay. We can check that one off as probably okay. As we move down through here, we see that the voltage of 7.09 is shared across each one of these two branches here, 7.09, 7.09. And we measure current down both of those branches. 40.9 comes into the node. And we see that it's 35.5 milliamps going towards this 200 ohm resistor to ground. That one should have the most resistance. Yet again, we expected this whole parallel series combo down here to be much larger than that branch. So as we measure the current down this other branch, we should have what's left over. So we do. We have 40.9. We lost 35.5. We have left over 5.42. We should see that that travels all the way through to the other side of this resistor. So we do have that. So far it has current. We just need to make sure that that series component, that 440 plus, actually has a voltage drop. So we'll measure on top. We got 7.09 on top from the node voltage. On the bottom, 4.71. So we have a voltage drop. We have a current flow. So we now know the 440 and the 200 are probably both okay. And we need to keep going in our diagnosis here. So we know that 4.71 volts leads us into this node here, and that is shared across both of these two branches here, 4.71, 4.71. We'll grab our current probe. We see that 5.42 milliamps comes in, measure across each one of these branches. This one gets 0 out of that 5 amps, and 5.42 milliamps goes directly through this 870 ohm resistor. Right, so we're not deciding to change anything. We're almost having like a series path that leads us all the way to ground right here. And it's almost like this resistor here doesn't exist at all. Right, we get 0 amps coming down that branch, which means that this resistor here must be such a large resistance that it's stopping all current flow from becoming paralleled right there. And so we're not dividing any current towards it because it's such a larger pathway. And the least resistive path would lead us directly through this 870 ohm resistor. So our fault is this 680 ohm, and it is open. So note that we're not measuring any resistances in this because we're focusing on live current faults, live voltage faults. So those are all live circuit measurements, and we want to stick with live circuit measurements when we're going after our components in this example here. All right, let us know if you have any questions.